Hello, my name is Mauricio. I work at Delft University of Technology in the Software Engineering Research Group. And this is a talk I'm going to give at the CHOSE Forum, which is a Swiss forum in software engineering. I'm also going to give this talk at MSR Asia this December. And this is just a rehearsal. I'm doing this from home, so you might hear my dog from time to time, but that should be fine. So I call this talk Testing in Production, a Gentle Walk on Software Monitoring. And my goal is to basically try to show you what industry has been doing in terms of monitoring, as well as what industry has been doing in terms of monitoring. Why do we care about monitoring? So if we think about the tech companies that we have nowadays, they have two interesting characteristics. So the first one is that they try as much as possible to maximize the return of investment, or to have the return of investment as soon as possible, or to create momentum of their new technology as soon as possible, right? And for this to happen, they have to move fast. And by moving fast, I mean they have to keep deploying software very fast. And the type of software that they create is not simple, it's highly complex, which means that although they try as much as possible to do all the best testing possible, the failures are just too tricky to be predicted. I think this overall move fast thing became really popular when Mark said something like move fast and break things, and I think this was the message he was trying to give to people, right? So if you want to be competitive, you have to move fast, and if you're moving just too fast, well, things will break from time to time, and we just have to embrace this and make sure that those bugs, they don't really affect us, and we can detect those bugs as soon as possible. And this is how I interpret this. And to make this move fast possible, something new in software engineering has become a first-class citizen, which is monitoring. So companies are more and more now focusing on amazing monitoring pipelines, so that if a mistake happens in production, they know it as soon as possible and they can take action. And a nice way to see how industry has been adopting this, from my point of view, is to just see the number of companies that have been proposing products that help developers in monitoring their software. So Elastic, for example, the creator of the Elk stack, which is a very popular one, but you see many others, right? Like Splunk, Sumo Logic, Loggly, so on and so forth. You also see these in the media, right? In developers' media, like for example, Martin Fowler's blog has an entry there, a wiki page that is called QA in production. In Medium, you can find articles like testing in production the safe way, and they are not really saying for you to test in production, right? That's crazy, but it's more like you should monitor your production environment and make sure that you learn from it. So this is an interesting trend. And I'm going to also give some context to my talk. And this context is given by one of our industry partners at Delft, which is Adyen. Adyen is this Dutch unicorn that does payments. So Adyen is basically a layer that helps merchants in paying their goods all over the world, right? So you're a company, you have your amazing service, and you want people from all over the world to consume your services. But you don't want to integrate with every single payment method that there is, right? So Adyen does this business for you. Adyen integrates with all the banks all over the world, and for you as a company, you just connect to Adyen, and that's it. Adyen has 3,500 customers all over the world, including big companies like eBay, Uber, Spotify, and Facebook. The valuation of the company was 2.3 billion, making Adyen actually the largest Dutch unicorn. In 2017, Adyen became also a bank in Europe, and Adyen has more than 1,000 employees for 80 different countries, and Adyen has processed more than 160 billion euros in payments. So they are this very large company doing complex business, and monitoring is something fundamental for them, right? If payment goes wrong, people are not really buying what they want to buy, the world crashes. To support my discussion, we have been thinking a lot about software monitoring logging research, And everything that I say in here will be backed up by the systematic literature review we conducted. If you go to Google Scholar, ACM, IEEE libraries, and you just start to look for papers on log analysis and these kind of things, you find lots of papers, and you can see that many different areas are actually using logs to learn something, right? We see papers from medicine collecting logs from medical devices and these kind of things. We try to focus on software engineering type of papers. We then did another filtering, which is we focused on A star and A conferences, and this gave us around 100 papers on all sorts of topics, which is something that I'm going to present very soon. And if you see the picture below, you can see that the number of publications are actually increasing, right? So the topics becoming more and more hot, important in our community. Our literature review is actually submitted right now, and I think one of our main contributions there was to first explain how log works or how monitoring works for a very large company. This figure created by Jean, our PhD student. I'm not sure if you can hear my dog. They are making big noises in here. I'm sorry for that. But so in this picture, we start with the log generation. Or log engineering, let me call it like this. So the developer is there, he or she is programming the software, and at some point the developer needs to decide that, well, I need a log line in here. And those decisions, which I'm going to discuss very soon, are quite tricky, and there are lots of papers trying to tackle or to help developers there, right? So how to engineer log lines. But then you wrote your log lines, you deploy your software goes to production, and these log lines that you have in your Java application start to become log entries somewhere in your system, right? And all this log data, it's usually, well, inserted into some sort of storage to store this massive amount of data that we have. This storage not only knows how to store massive data, but also gives you query functionality, so we can explore this a bit. We're going to focus on the log infrastructure part, and we're going to also discuss the log analysis, which is as soon as those log data they are stored, we want to do analysis on top of it, right? We want to learn from this data. This is what we call log analysis. And we also saw a fourth type of paper, which is we call log platforms, which are papers that are trying to tackle all those problems together, right? Usually more from the tool perspective, from the human perspective, developers using those tools and learning from those tools. If we dive a little bit more into it, which is what I'm going to do very soon, so we have the four categories that I discussed: log engineering, log infrastructure, log platforms, and log analysis. And what we did was we read those 100 papers, and we tried to come up with categories that explain the problem or what those papers are trying to do. So let's go one by one, because this is going to be interesting. So log engineering. As I said, you as a developer, you have to engineer log lines. And this is tricky because you have to consider what to log, where to log, right, in your source code, how severe the log level should be. So log4j allows you to choose, well, this is just information, this is just debugging, or this is a big error in your system. And it's tricky because you have a code base of millions and millions of lines of code, and you have to find the precise spots where log will give you information in case of an anomaly, right? Empirical research actually shows that around 3% of lines in your source code are related to logging. One of my students also explored logs in the Apache community, and we found that around 6% of methods in there have at least one log line. So those decisions matter, right? And again, let me reinforce this. It's a big trade-off for you because you don't want to log too much, because otherwise you're going to have to think of big storage. Your log will be bloated with lots of useless information. But you also don't want to log too little, right? Because otherwise when there's a crash and then you start to debug the crash, maybe your logs that you have don't really help you to debug. And researching there, or papers on this area, they have been focusing on first anti-patterns in logging code, so bad things developers can do in their log lines. helping you to implement your log statement, so trying to help you in taking the decision of where to log, even what to log, and then some empirical studies more related to what those logs look like in general. So just to summarize a little bit of those papers for you, so what type of common log engineering problems those papers talk about. So improper log message, so you write a log message, but then you soon realize that this log message was not good enough, and you have to change this log message to improve it. You choose an improper log level, so this needs to be debugged, but you put it as an info, so those things get really messy when analyzing the data. Something really interesting that came up when discussing log with large companies, and in specific Adyen, if you think about a very big organization, maybe a log line has one level for one team and another level for another team, right? So think of team payments, maybe an exception, a log line there, it's very important, so they see this as a fatal log level, but maybe for the reporting team, that's less interesting, right? Maybe this is just a debug logging or so. So in very large software, even deciding which stakeholder has priority when deciding the log level can be tricky. You might have runtime and configuration errors, right? Logging is code. Your logging code might throw a new pointer exception, for example. Or you might have configuration errors related to how you're configuring your logging infrastructure pipeline. And I discussed about this already. You're missing log statements, you didn't log enough, or you logged too much. If I can give you one concrete example of an empirical study in logging, this one was conducted by us at Adyen, and mainly by Joop, that you can, the person you see in the picture. So Adyen has this very large web service where all the customers integrate, and this web service is the integration point between the company, between the merchants and Adyen. So they want this integration to be as smooth as possible. And if you think about it, they have thousands of customers. Those people are sending thousands of requests per second, and a lot of exceptions happen, right? So we were very curious about what kind of exceptions we see there, so that maybe we can learn from these exceptions and improve our logging pipeline, right? So payment APIs are very, very complex. This is a boundary of our problem, right? We're not talking about an API that receives 1 or 2 parameters. We're talking about APIs that receive 50, 100 parameters in one call. That's how complicated payments are. Merchants, right, the people doing integration, they might not notice the mistakes, right? Or because it's just too complicated. So what we did was we collected around 2.5 million error messages. No. So these were the number of mistakes we had back then. In this paper, I think we collected around 1 million. And we did some manual analysis in there. Of course, we aggregated these exceptions and we did some manual analysis in there to kind of understand the underlying issue behind that problem. And we came up with this table that is very human readable after months of analysis. And we separated the mistakes according to the stakeholders that might cause the mistake. So the first one is the end user, so us. So when we are trying to buy a product online, for example, we type some information. And this information, if you type your name where you should type your credit card number, that might cause a problem, right? Maybe you send this information to the merchant sends it directly to us, to Adyen, and then this causes the exception. So we separated this into end user mistakes, API consumer mistakes, so the merchant, so the company doing the integration with us, internal mistakes, so mistakes actually caused by Adyen software, and third-party mistakes, because Adyen at the end of the day also talks to banks, right, to ask authorization for a debit, for example. And interestingly, if you pay attention to these numbers, we see that most of the exceptions are actually caused by the integrators. For example, in the request, they just send invalid data. Yeah, this invalid data might be in some strange format. It throws an exception in our system. The payment is never concluded, right? Or they're missing some information. So if you're doing payments in different countries require different information. The merchant might miss one of them. This throws an exception. And so these are the kind of exceptions we cannot really fix from, Agile cannot really fix from their side, right? They can, of course, give you better error messages, they can improve documentation, but this is not something that is wrong with their software. When it comes to their software, you see that it's actually a very small amount of percent in there that is, a mistake by their side. And this is expected, right? They are a very big company with a very robust software. But maybe these are the exceptions that we should care about, right? So, in a way, think about the number of exceptions these companies getting per month, and the number of exceptions that they can actually really do bug fixing about. So it's very small, right? And this means that in that overwhelming amount of data, you have to find, what really matters to you or what kind of bugs you can really fix. So this is a type of problem thing that happens when you're doing log analysis, right? You have lots of data and you have to find what's interesting to you. So that's tricky. Coming back to how can we support developers in doing better log engineering, machine learning is something that is going more popular everywhere, right? And in the logging field, it's the same. So this paper, for example, the one that I'm showing, authors, they try to train models that are able to predict where you should log something. Models are, in this paper in particular, are using, well, I'm going to call it traditional machine learning. So they do some feature engineering there. They train different models and they see how the prediction goes. And results are actually pretty good, actually. And the authors even conclude that we believe our work can serve as an important first step towards the goal of learning to log. And I completely agree on this. So I think this is a beautiful area of research. Can we build models that really point to developers where they should log, right? Or help developers in taking this decision. Can we try with deep learning, right? Because whenever you're doing feature engineering, maybe your model has your bias. Can we see if we can let the machine learn what matters in terms of when taking this decision? And we tried a little bit about it. This is totally experimental. What we like about deep learning is that maybe you can feed the source code in a way that the model not only learns about the structure, but also the semantics, right? The meanings of the variables there. We did our first exploration. In there, we tried with simple natural language processing techniques, feeding just words to an LSTM, for example. We also tried something a bit more interesting, for example, feeding random walks of the AST, like for example Code2Vec does. But the best we got was 71% of balanced accuracy. Why balanced accuracy? Well, the problem is very imbalanced, right? You have way more methods that you don't log, or places you don't log, than you have places that you log. But this was just our first exploration, right? And this shows that this is actually a complicated, or this shows to me that this is actually a complicated problem. But there's lots to be improved there. This was a master project that our students started, and we're continuing on this. So wait a little bit more, and we're going to show you some pretty cool results on this. Now I'm moving to the next part, which is logging infrastructure. So the developer already engineered a lot of logging code. This logging is being executed in production, data comes, you have to do something with this data, right? And this is what we call infrastructure. And we see two types of different papers in there. So the first one is focused on storing this data and even compressing this data because it's just too much, right? I think we could have more work in there. And that's one point. The other point is we see lots of papers on log parsing. And this is something I never really thought about before joining a big company and before reading papers about it. So if you think that logs are being generated and logs are usually very unstructured, you have to parse these logs to a better format before you can start doing some queries. Just think of your log4j lines, right? They're just lines. Maybe you have the class name, you have the line number, you have the message. This message contains a static part and a variable part, and you want to break those things. This is very tricky. Or imagine a log that you don't control so much. You're using MySQL. You're not going to really change MySQL source code to improve the logs. So MySQL logs in its own format, and you want to parse this to a better format that you can query. So that we see lots of work, and believe it or not, big companies do require this log parsing as a step before doing something. And I'm going to give you an example that actually happened at Agen, and this even became a master thesis done by Dan. So this is just a log4j message, right? Static part mixed a little bit with variable parts. And this is just how a normal log4j output would look like. So you have the timestamp, class, the line number, then the message. The tricky thing is that logging the line number is quite expensive in log4j. It takes log4j 20 milliseconds more than if you compare when you're not really logging the line number. And 20 milliseconds per log line times a billion times those methods are executed, this is just a bit too expensive. And very large pipelines, very large companies cannot really afford this, right? So those logging pipelines, they avoid logging the line number. That's really expensive. I put here an issue that is discussed in the log4j2 repository, and it's a very interesting discussion. They are discussing how should we get the log line. Should we try thread.currentThread.getStackTrace, or is it better to throw an exception and get the stack trace? And believe it or not, in Java, for some reason, for the VMs that they were playing with, neutral.getStackTrace is faster. It's faster to create an exception and then get the stack trace than just asking your current thread about the stack trace. Crazy stuff, right? So lots of engineering work needs to be done here so that maybe we can solve this problem, right? So that maybe that's a beautiful master thesis for someone. So that's what I said. So you cannot really afford printing the line number. The class, well, it's quite cheap because in log4j you have to declare the class that you're logging. So this is kind of static information. The line number is pretty expensive. So can we actually then start linking or tracing what we see in the raw data in your log storage to the source code? We don't have line numbers, right? And these are just text, and this is like log4j lines. Can we come up with this connection? Because if we can, then this starts to enable us to do some automated analysis, right? So this is the log line that generates this information into my software. There's a very nice paper that we used as an inspiration. That's what they tried to do as part of what they call detecting large-scale system problems by mining console logs. They propose an approach there that we were very influenced, and our approach at the end looked like this. So you have your very large source code base. In case of Agen, I cannot really say the number of lines, but it's on the scale of millions and millions, of course. We have a step before, which is we parse this source code, we find all the log statements. We then start to create regular expression templates for each log line that we see. So for example, the log info that you see below, customer, then it comes a variable ID, and then another variable should become a regex like that, right? And we do this in two steps. So the first one, we build the generic template. Generic in terms of, as soon as there's a variable, we just put .star, which is in regex language, whatever. Then we enrich this template by, for example, well, if this is an integer variable that I'm printing, then I don't have to put dot, I can put /d, right? Then I will only receive numbers. We try to do this as much as possible. Our approach is even smart enough to visit the two-string declarations of methods. We try to learn from those two strings so that our regexes get even more precise. As soon as those templates are done, so logline template, we create an index because we need to search those things very fast in production. And then as soon as we have this database, we then go to our logging environment and log data comes. And then we pass this log data and we try to find which regex match matches these the log data that is coming in, right? And the one that matches the better, we say, well, this was produced by this. And we do this on the fly. In terms of accuracy, we try this in 100,000 messages that was generated in 1 weekday. These 100K messages pointed to 676 different locations in the source code. Then we did some manual analysis to see if those links were correct. Our manual investigation shows a very good accuracy, actually 97%, which matches similarly to the accuracy of the original paper. So this really works, and this scales, but with a grain of salt. So when we started to dive into the performance, we saw that building the ASTs is the most expensive part, right? So finding log statements, so we are counting building the ASTs and then starting to look for log statements. And it takes the big part of building those templates, right? And this problem gets more complicated because, you know, developers are changing their software all the time. So what was here before then starts to, you know, change the line. So maybe the information you had starts to change. We did some heuristics there to make sure that if the developer is like just moving the line around, this wouldn't break the model that we have. But if you change the log line, then, well, we just changed the regex needs to change, right? And then you have the difference between what you have in your source code base and what was deployed. So if you want to show real-time information and not information about the commit that was deployed, this gets even trickier, right? So still, although this approach works and well, it kind of scales, right? 40 minutes in a code base like Agent, okay, we can pay this, but there's lots of engineering to make this work in real time, right? When does it fail? Well, sometimes developers log JSON-based information, so log.info and then a JSON blob, and then, well, what kind of regex can we generate there? We generate a very generic regex and pretty hard to track it back, right? Unknown logging method. So we need to identify lines that are related to logs, and we do this by lots of heuristics. Like for example, if your object is a type of log4j object, well, this is a logging thing. But sometimes developers add layers on top of layers on top of layers, right? And they create their own logs. And then it's pretty hard to detect in a static way that those lines are log related, right? In the tool, what we did was we allowed developers to kind of point to the logging infrastructure that they have or log methods. That's the easy way out, right, for us. Log strings created on the fly, this happens a lot as well. So the developer wants to write a more complex log message, and then to do this, the developer starts to build strings, complicated strings, like in concatenating strings. And this just makes our analysis way harder, right? We need to understand that this log line uses this variable is a string composed of many different things, and then maybe, you know, you can go crazy on this, right? Maybe there are ifs that are used to build this string, and then you start to have multiple regexes for one log line, and so lots of engineering to fix this. Related work, so the paper that we are using as an inspiration, they have a similar discussion in there, and they say that almost all of the failed messages contain long string variables, right? So the variable part of the log message is just a very long string, and then regexes just start to fail. So that's it for log infrastructure. Let's discuss log analysis. So log analysis is that part of the figure. So log data is stored in a nice place, and now we want to learn, extract knowledge from these data. What kind of knowledge are people exploring? We saw anomaly detection. So anomalies happen, but common behavior happens way more, right? And how do you detect those anomalies? So this is what those papers try to focus. A lot of machine learning, as you can imagine there. But you see people doing research on using those logs to understand better the security and the privacy of the system, to do root cause analysis, right? So if you find the anomaly, this is the first step, but then you have to understand what causes this anomaly. And that's the root cause analysis, right? predicting failures. Maybe you can learn from the failures of the past that you see in the logs to predict future failures. You can use those logs to improve your testing. You can use those logs to try to build models that represent your software and maybe learn variants from those models that can help you again in finding anomalies, in improving the quality of your system in general, and reliability and dependability. In here, we were more focused on, or papers were more focused on non-functional requirements like performance. Challenges that we see there is that you see an avalanche of different machine learning techniques, or techniques in general, so supervised and unsupervised machine learning, passive learning, and state machines. I'm going to talk more about this because I really like this. And more recently, deep learning techniques. What we notice in there is that papers actually discuss this, that no single technique works for all the cases. So although we're learning what kind of models work better in specific types of problems, this is not a given, right? So there's always, maybe it's going to change for your context. So maybe you're going to have to do your exploration based on, of course, what you learn from research so that you build the best model for you. I think from the research perspective, we lack more representative data sets. There is this beautiful initiative by LogPAI, a very big research project in Asia, and they are collecting all log data that they find in papers and put them into a single repo so that researchers can use it more easily. But still, I kind of miss some sort of enterprise industrial logs in there. If you look at those, they are mostly infrastructure logs, right? And I think to me the big characteristic or the big difference between infrastructure logs and logs I see in industry is that, if you look at Hadoop generates in the logs maybe 50 different events, right? But an industry, a company has like 30,000, 40,000 different log lines, and each one of them representing one different event, right? So it's just a different scale. It is pretty hard to have labeled data sets. And here I'm saying that there's just one labeled data set, which is Hadoop. That is not really true because I didn't explore all of these, so I need to fix this in my presentation, but having labeled data sets is very tricky because someone has to label those, right? You're generating lots of data on the scale of millions or billions, and you need to label those if you want to train those models. And that's a big challenge, yeah? Cool. So talking about passive learning and model inference, this is one area of research that I see a lot of future that I like very much. We are trying to apply as I'm going to show. And model inferences, again, you have logs and you try to build models or state machines that represent the behavior of your system, right? And if you have such a model, you can do different things. The person that I like a lot in our community doing this is Ivan, the guy in the picture. And he has two amazing papers that influenced us a lot. And the first one is about given logs can be mined temporal invariants. For example, A always happens after B. This kind of things, right? And the other one is using logs to infer models of concurrent systems. We actually tried a similar approach because we also have this knowledge in our group. So Sikko Verwer, the researcher at the top, published an amazing paper on how to do passive learning. Sikko focuses a lot on security and trying to build models out of network protocols, for example. And we tried to apply those techniques at Agen, and Rick was our master student doing this. Rick collected hundreds of logs from their embedded systems. Those embedded systems generate logs that look like this. So from when you put your card to the payment being accepted or not, you have like 30 to 40 different log lines or events that might happen. And Rick collected hundreds of those and start to build very large state machines. And of course, as I put in the slide, the smallest modular state machine possible. And I'm going to get to that because this is where scalability starts to become an issue. And we started to build those state machines. We started to minimize those state machines so that humans could read. And then we were giving those state machines to experts. And to our surprise, experts were able to start pointing things that were not so okay in the software. For example, in this picture, in this model in particular, so we noticed that there was one behavior in the app that was ask for your PIN, your password, and then ask for the signature. This is actually an unwanted behavior, because if you type your password, you don't need signature. And then the experts said, oh my god, this is a bug, let's fix it. And actually they were able to fix this before this went to production. So this was really nice. We then started to build different state machines for different use cases there. So Agent talks to different banks or acquirers, and we started to build state machines for the different banks and etc. to see if they would behave differently. We would expect them to behave the same, right, in terms of transactions being accepted or transactions being denied, so the proportion should be the same. But then we started to notice that for one case, we had twice as many chip errors. So when you're trying a transaction with your credit card chip, we saw more errors in A than in B. We actually informed the merchant about the situation, and at some point we discovered that the bug was actually on the acquirer's side, on the bank side, and we notified the bank, and they were actually able to fix the software on their side. So this is how cool those models can be. Timeout, so if you start to add more information into those edges, for example, the time it takes from event A to event B, then you can learn performance things, right? So, and in this case in particular, what they notice is that in some places where all over the world where 3G is not very good, well, the connection takes so long that the software was given a timeout and the software was saying payment rejected. And so what developers learned from this is that, well, maybe we should have better retry mechanisms there, focused on specific regions that they know 3G is still not so good. But scalability is needed there. So first, to ingest a huge amount of logs and build state machines, this is not so easy to be done, right? In terms of scalability, building graphs in scale. The second one is, if you try to build the smallest model possible, you need to start merging two states, right? So if you see that A always happens together with B, you have to be confident enough that this is true, right? And it's true in terms of, you know, down there in the graph, this is still true. Then you can merge these and make this into two states, right? And in the passive learning community, they do this because this is also a way to generalize those models, to make them less specific to the data you are observing, which is something we want in other models. But those algorithms are quite expensive, maybe n squared. So doing this in scale is tricky. And what we're trying to do is to use all fancy streaming technologies. This is done by Rick, our master student, together with Asterios, our assistant professor, and he knows everything that is to know about streamings and large-scale data processing. And this is what our solution looks like. So you have your distributed system generating logs. Those logs are collected. This is usually already done by companies, and then we send those things to message brokers. Those message brokers, the first step is to do aggregation, because you're producing log events, but we want to aggregate them by, for example, one transaction or one customer. And you know, because those things are distributed, then lots of things happen in a synchronous way. You have to wait until everything is concluded. So we wait. As soon as one transaction is completed, we aggregate, we send it back to the message broker. It goes to a prefix tree generator that we have many, and we start to build partial prefix trees. As soon as we have many prefix trees and we are happy, we just send those partial prefix trees back to the message broker, and then this is then collected by the big prefix tree aggregator that tries to merge all the prefix trees into one big prefix tree, which we then insert into a database so that anyone can query the current version of the state machine, right? In terms of technologies, we're using cool stuff. FluentD and Logstash, this is what industry uses to collect the logs from their systems. They send it to a message broker, Kafka or NATS. We then use Flink as a streaming tool behind the scenes, and we use Neo4j as a graph database. So where we are right now, implementation almost done. A lot of tricky things we had to do to make this to work, a lot of plumbing, but this is working. We're now doing a controlled evaluation to see how much this scales. We are aiming at billions and billions of log lines, because that's where industry is. I'm going to talk to you about this very soon. And then we're going to apply this into a case study. So Rick is doing his master's in a company, in a startup. But besides being a startup, they are already producing a huge amount of logs. And we're going to try it. Future work state merging, right? So we have some ideas on how to do state merging in scale, but this is something that's going to be work for our next student. One more example of log analysis that we have conducted, and this was in partnership with SUTD, so the university in Singapore, done by Herman. Herman was also a master's student. So cyber physical systems, they also generate a lot of logs. And this one in particular is a water management station. So it basically gets, well, salty water in one end, and it produces drinkable water on the other hand. And this is done by lots of hardware, right? Cool engineering stuff. And when you go to understand this hardware in particular, this system in particular, you see lots of sensors and actuators there. So sensors are trying to understand what's going on, and in a part of this, the process, as the sensor learns something, the actuator sees what's going on with the sensor and then takes a decision. For example, the tank is full of water, maybe we should send water to the next tank, and then the actuator then opens the other tank. But you know, we have hackers, and hackers are trying to get control of those sensors. And what we try to do is, well, let's see if we can build machine learning models that would be able to detect whether a sensor is acting in a strange way. So what we did was we actually hacked each one of those sensors. So we removed the sensor, we put a simulation in there. This sensor started to generate bad data, so to say, and we monitored the whole process there and collected the data to see how the whole process looks like. We then started to train machine learning models, right? So we had data of normal traces. We put this monster to run for 4.5 hours. We then simulated our attacks in 3 or 4 different sensors for like 3 hours as well. We started to build feature vectors in, well, this is not so correct to say, but seeing this as a time series, right? So 90 seconds of data, this is what we wanted to insert to the model. Related work tries to do this at line level, so those systems generate logs every few milliseconds or so, and they try to predict at millisecond level. This doesn't make a lot of sense to us. We're like, our intuition was you have to give some sort of notion of time series to the model. That's what we try to do, but in a very naive way. We trained machine learning models, and yeah, the accuracy was actually very good. But there's lots of future work to be done. We did this in 3 months. It's not so easy to get access to these beasts, and these beasts cost money to run. So yeah, lots of things to improve. But this is the type of analysis you can do as soon as you have log data, right? This is nice testing. Finally, a paper that I like very much, not part of our literature review because it was published this year at FSC from the folks of Microsoft Research. This paper is basically a deep learning model that tries to find anomaly. But what I like from this model is that it understands that log lines change over time. So we have a log line. If the developer makes a small change in there, maybe this small change will break all the models you built. And those folks are basically showing that if you build a model using some deep learning interesting techniques, those models are able to ignore such small variances that might happen in a log, right? Like changing a small part of the log or adding one log line in between 2 log lines that you had before. So when I read this paper, I felt it was, yes, that's the way to go, because it takes a real assumption in the approach, right? And the assumption is that log lines evolve, and they evolve very, very fast. So the log lines you see today, they're going to be different from the log lines you see tomorrow, even in terms of structure. Finally, last category, log platforms, and the goal there is to focus on the integration of all the dimensions. We don't see a lot of papers there, they're quite too focused, but we do see a lot of interesting stuff to be done in there. And now, I'm going to focus this discussion on the human perspective, you know, as soon as all those things are plumbed, so all the techniques for log engineering, parsing, storage, analysis are, plumbed together, we need to show this information to humans, right? And this information should help humans in taking decisions. One small piece of work we did together with Ajin is done by Jos, our master student, is that we noticed that developers, they have this sense of, they're DevOps, right? They do devs and they also care a lot about ops. So when their software, their module is deployed, they actually monitor their modules to see how how the software is behaving, right? Their specific part is behaving. How do they do it? Well, they go to the IDE, they program, software goes to production, then they have to quit the IDE, go to the monitoring tool and start to do queries in the monitoring tool. They find problems, they go back to the IDE and they keep going back and forth. So we thought, well, IDE, integrated development environment, it is an integrated development environment for a reason. So why not putting these two informations together, right? Let's connect the monitoring tools with the development tools. And we built a small prototype. It looked like this. So we enhanced IntelliJ, and whenever there was a log line in there or an exception, we were basically showing how often that exception or that log line was happening real time. So these numbers were getting updated. So information comes into the production. We were doing some massaging into this data using actually the parsing tool we discussed before, and then sending this data back to the IDE. We were also giving other type of information that developers like to see. For example, not only the number of exceptions, it has happened in the last 24 hours, week, so on and so forth, so that they have more information to take a decision. They could do some basic queries there as well, maybe look at per class or something like that. And if that was not enough, you could quickly click on one of those squares and we would send you directly to the monitoring tool already opened in that log line, and we write the query for you and these kind of things. So more of an HCI type of thing. We deployed this for 12 developers for 4 weeks to see just how they would use this. We noticed that we were actually showing a lot of information to these people. So for one of the participants, we noticed that this person, our tool showed more than 600 different information to this person. So yeah, they were using it. It's pretty hard to say if they were actually looking to the information, but we were showing the information. They were requesting, so to say, the information, or it was there for them to see. But then we also asked them, after the week of work, you saw this information. Did they really impact you? What did you learn from this information? Did you learn something? And in a lot of cases, they said, this had an impact on us. And what really was a surprise to me is that the main thing was that they understood the business process a bit better. So in large-scale systems, no one really knows the entire thing. So they use the logs as a way to understand how the software really behaves into production, because the variability, the complexity is just too big. So logs also have this, perspective of code comprehension, program comprehension that I never thought about. They also use it a lot to understand the implementation stability, so they're deploying very often, and performance and scalability is crucial for them, so they actually follow the deployment. So they deploy the software and then they go to the source code to see how it is really behaving, right? Is my new feature stable or is it throwing lots of new exceptions? Identifying bugs and these kind of things, it happened a bit less, but also because, Agile is pretty robust. They don't have bugs every day, So this is kind of an anomaly situation. But still, they were able to, in 3 opportunities in these 4 weeks, our information helped them to debug and find bugs. Plus personal perceptions, less context switching because you don't have to keep going back and forth from the IDE and monitoring tool, less cognitive load, and etc. So that's it. These are the 4 big areas of research in log analysis. And now I want to conclude my talk by discussing some opportunities for future work where we see we can still improve. So from the log engineering part, I really think we should help developers in deciding where and what to log. And AI or AI techniques for software engineering problems, they have been having amazing results, right? So I would say we should do more AI for log engineering tasks. Log infrastructure, we should put scalability and real-time analysis as first-class citizens. And we see, papers discuss in the scale of thousands of log lines and even millions of log lines, but the scale nowadays is billions of log lines. So Agile is in the billions scale, and it's not 1 billion, it's not 10 billions. I promise you, it's way more than that, and it's going to be trillions, very soon. If you see Agile is doubling every year, so we're just doubling these numbers. It's really crazy. So you have to think of billions and maybe trillions. Log analysis, the scalability and real-time things also apply here. So your approach needs to work for billions of log messages. But I think from the research part, we see that we need more systematic comparisons among the different approaches. People have been producing a lot, but there's no real paper actually trying to put them together, right? So I think we need at some point to start connecting all the knowledge that we have been creating so fast. And I think we also need to embrace unlabeled data. So when you go to those data sets, creating labeled data sets is pretty expensive, right? I mean, how can you really ask someone to label millions or billions of log lines? Some data sets, some companies can do. So this Microsoft paper, they actually were able to label thousands of data points, but that's not just a few companies in the world can afford this, right? So I think we need to embrace that we don't have labeled data and try to think out of the box. Maybe, for example, unsupervised learning or semi-supervised learning, because this is a big issue if you're doing research at an university. Label data sets. Finally, log platforms, and in here I'm going to focus on us trying to deploy our tools for companies and for humans to use. I think we need to have better standards when it comes to logging tools. It's just pretty hard for us to deploy any tool that we build in a place, right? Because those logging infrastructures are so specific to a company that you have to do lots of small customizations to make things to happen. And I know standards are boring and they add a layer of a complexity there, but maybe if we had this layer, it would be very easy for people to just start deploying their tools as plugins, right? So that's it. And before I close it, I want to thank all my colleagues. This has been work. We have been doing this for many years, and many people helped us to build this knowledge. And these names are in order as well as in the picture. So thank you so much for Jean, for Joop, for Jos, for Rick, for Dan, for Ari, for Jurgen, for Siko, for Herman, and for Asterios. To summarize, so monitoring is a first-class citizen in contemporary software development. We classified log research in 4 different topics: log engineering, analysis, infrastructure, and platforms. We are moving really fast, and that's very good. Open challenges, the unstable, unstructured, and unlabeled data that we have, the need for scalability, think of billions and trillions, and the need for better standards. And also something for researchers. I think a lot of those things, they take us months and months of work because of the engineering part. If you want to build something that scales, you're going to suffer to program a tool like that. So there's lots of engineering work that needs to happen before good research can happen. And I think our community should value this engineering work a bit more so that we can really spend our time on these things. You can use my presentation if you want, just read the license. And that's it. Thank you so much.